Hi there. Today we're exploring the Monotone Convergence Theorem, or MCT. It's the secret engine behind how we determine if infinite series add up to a finite number. Let's get started. An infinite series is essentially a sum of infinitely many terms. We write it as a 1 plus a2 plus a 3, and so on, continuing forever. Since we cannot actually reach infinity, we look at partial sums. We sum up to the first term, then the first two terms, then the first three, and so on. This creates a sequence of values that tells us how our series behaves. The core idea is simple. The sum of the entire infinite series is just the limit of these partial sums as the number of terms grows without bound. To understand infinite series, we start with the concept of partial sums. Instead of adding every single term at once, we keep a running total. We define Sk as the sum of the first k terms of our sequence. S1 is just the first term, S2 is the first plus the second, and so on. A series converges if the sequence of these partial sums eventually settles down to a specific finite value as k approaches infinity. A sequence is bounded above if there is a number m that the sum never exceeds. Imagine a ceiling that the values can approach, but never touch or cross. If our partial sums are strictly increasing, they are constantly climbing upward, but as long as they stay below this boundary m, they are effectively trapped. Because the sequence is forced to stay within this space, it cannot increase forever. It must eventually settle at a specific limit. The monotone convergence theorem is a pillar of calculus. It states that if a sequence of real numbers is both monotonically increasing and bounded above, then that sequence must converge to a finite limit. Think of it this way. If your sequence is always climbing, but there's a strict ceiling it can never cross, it has to settle somewhere. It effectively gets trapped by that upper bound. Whenever you can prove these two simple conditions, you don't even need to know the final limit to be certain that the series behaves reliably. That is the true power of the theorem. We are tackling the famous Basel problem. We want to prove that the infinite series of the sum of 1 over n squared converges. The question is, can we prove this series is finite even before we know its exact value? This is where the monotone convergence theorem shines. To use the theorem, we only need two things: show the series is monotonically increasing and show it is bounded above. Let's start by looking at these partial sums. To prove our series converges using the monotone convergence theorem, we first check if the partial sums are increasing. Our series consists of terms 1 over k squared, which are always positive. When we add a positive value to a partial sum, the total must get larger. Each new term adds more height to our sum, creating a strictly increasing sequence. Because each term is greater than 0, our sequence of partial sums never turns back. This monotonicity is the first requirement satisfied for the monotone convergence theorem. Now we need to show our partial sums don't grow to infinity. Even if we add infinitely many terms, the sum stays limited. We use a clever comparison trick. Notice that for n greater than 1, 1 over n squared is strictly less than 1 over n times n minus 1. This comparison is the key. By replacing our terms with this simpler fraction, we can bound the growth of our sum. This technique effectively caps the total value, proving that the sequence of partial sums will never exceed a specific real number. To simplify our series, we use partial fraction decomposition. This is a powerful algebraic technique. We start with the expression 1 over n times n minus 1. We can rewrite this expression as the difference of two fractions, 1 over n minus 1 minus 1 over n. This is the secret to unlocking the telescoping nature of the sum. By splitting this fraction, we set the stage for terms to cancel out perfectly in the next steps. When we write out the partial sum sk using this identity, we get terms like 1 minus 1 half, plus 1 half minus 1 third, plus 1 third minus 1 fourth. Notice the pattern? Look closely at those adjacent terms, the negative 1 half and positive 1 half followed by the negative 1 third and positive 1 third. They are ready to disappear. Now that we have established that our partial sums are monotonically increasing and bounded above by the number 2, we have satisfied both critical requirements of the monotone convergence theorem. Because the sequence of partial sums is trapped below 2, it cannot grow infinitely. Being forced to climb without an exit, it must settle into a specific value. Therefore, by the monotone convergence theorem, we confirm that our series converges to a finite limit. We don't even need to know the exact number yet. The theorem guarantees that the limit exists. We have established two critical facts about our partial sums. First, they are monotonically increasing. Second, they are bounded above by a constant. These two properties are exactly what the monotone convergence theorem requires. Because these conditions are met, the theorem guarantees the existence of a finite limit. The series converges. This conclusion is the ultimate goal in our series analysis, proving that our process behaves reliably. Here is the truly beautiful part of the monotone convergence theorem. We have successfully proven that our series converges to a finite value less than 2 without ever needing to calculate an infinite sum. This is an incredibly powerful shortcut in analysis. By simply verifying that our sequence is increasing and bounded, we unlock the truth about its behavior. We gain certainty without the heavy lifting of infinity. We have successfully used the monotone convergence theorem to show our series is bounded below 2. This gives us a safe limit. But what is the exact value? The actual sum is pi squared over 6. It is about 1.645. Finding this precise number is a classic challenge in mathematics. While calculating pi squared over 6 requires advanced techniques like Fourier series or complex analysis, the monotone convergence theorem provides the foundation. It tells us that our series behaves reliably and converges to a stable value, even before we know exactly what that value is. In the world of engineering, we rely on infinite processes to approximate physical realities. But how do we know if our computer simulations are actually providing a stable answer? Without a guarantee of convergence, numerical approximations might explode. Imagine an algorithm that never stops growing, exceeding its physical limits. We call this instability. The monotone convergence theorem acts like a mathematical guardrail. If we can prove our sequence of partial sums is monotone and bounded, we guarantee the process is safe and stable. Key takeaway for engineers: MCT ensures reliability. It tells us that our approximation will land on a specific finite value rather than drifting off into errors. Today, mathematicians use advanced software called proof assistants like Lean or Coq to formally verify theorems. By inputting logical steps into these tools, they ensure every part of a proof is airtight from the ground up. These tools eliminate human error and help provide absolute certainty in complex mathematical logic. To use the monotone convergence theorem effectively, we follow a reliable logical workflow. Let's look at the steps. Step 1. Define the sequence of partial sums. Step 2. Verify if the sequence is increasing. Step 3. Prove that the sequence is bounded. Step 4. Invoke MCT to guarantee convergence. Once these conditions are satisfied, the monotone convergence theorem guarantees that your infinite series will converge to a finite limit. The monotone convergence theorem isn't just for math classes. It is actually a powerful tool for computer scientists to analyze how fast algorithms run. When we write a recursive algorithm, every step takes a certain amount of time. If we look at the total work, we are often looking at the sum of an infinite series. By proving the series of work is bounded using the monotone convergence theorem, we can guarantee an upper bound on execution time. This is exactly how we determine big O notation. In short, MCT helps us prove that our code is efficient and reliable. It turns complex, infinite recursion into a simple, predictable performance bound. The monotone convergence theorem acts as your reliable partner in mathematical analysis. It fundamentally changes the goal from the often difficult task of finding an exact sum to the much more elegant task of proving that the process is stable and convergent. Thank you so much for joining me today to explore the power of the monotone convergence theorem. Keep practicing and keep exploring the beauty of analysis. See you next time.